Welcome back. Off we go. We have to know when we're looking at the strong nucleophile approach and when we're looking at the acid-catalyzed approach. I think the strong nucleophile approach is fairly self-explanatory. It occurs when there is a strong or medium. I believe in chapter 9 we called it moderate. During epoxide opening. And this other approach occurs when there is a strong acid present during the epoxide opening. I'm adding that last bit at the end because sometimes you're going to see a second step where there's a strong acid, but the epoxide's already going to be open during the epoxide opening. So it won't fit this category. That's another way of saying strong acid present in the beginning. Okay, so we'll look at the mechanism for these two. I wish I copied this before I started writing all over the place. Get a new page going. Nope, do that here. Not much to get rid of after all. And what we have here and down here, slightly different mechanisms. Okay, quite different. I've been using our fancy pens at all. Well, that's a little too fancy. Shadow. Okay. Strong nucleophile says, okay, remember what I said about opening triangles minutes ago? I said if there's a cation present, you should be thinking about which carbon better stabilizes carbocations. Do you see a carbocation or any cation at all present in this triangle? Answer, no. This is not governed by cation stability. Nucleophilic epoxide opening is governed by approachability. That's another way to say it's governed by steric factors. That's another way to say it's governed by which carbon is easier to approach, one that has no carbon groups attached or one that has a carbon group attached. The answer is the less substituted carbon is easier to approach. We're going to attack the less hindered carbon. I got red already. Let's go light pink. Attack least hindered carbon and oxygen gets a lone pair. Attack least hindered carbon. This is not about carbocations. We'll talk about carbocations in our next one. And you have generated an oxide. an alkoxide. Here's the original pieces. We have an O bond to carbon here still. And down here you have OCH3. Looks a lot like the product above it. There's a relationship between this and the product above it, other than the fact that a R became a P, which I just fixed. Let's see, what do we got here? Oh, this is the base version of this acid. Where's it going to get the proton? There's only one place, from the solvent. And in this example, after you react the solvent, you've generated OCH3 minus. So in this example, OCH3 minus can be thought of as a, let's see, we used it and we regenerated it. Catalyst here. The nucleophile will not always be a catalyst, but in this example, it fits the definition. Please finish the mechanism. O minus grabs H. Sigma becomes lone pair. There's your OCH3 minus. So a very straightforward mechanism. I know you like that mechanism. Opening epoxides, not a huge deal. Acid-cat approached. There's no way this thing is going to attack any of these carbons because it's not reactive enough. It's a poor nucleophile, not even a medium nucleophile. So it needs help. It needs an acid-catalyzed help. What are you going to protonate? Well, got to make the O leave one of the carbons. One way to do so is to protonate it using a strong acid such as HOTS. And now you will see there is a cation present. Now you can remember what I said about triangles where cations are present. What did I say about triangles where cations are present? It's all about which carbon spends more time with the carbon with a positive charge. Which one? More substituted carbon. Make that happen. That arrow by itself would generate a carbocation. But this reaction is such that as that's happening, the HOCH3 nucleophile, which is surrounding this molecule, because it's not just a nucleophile, it's a solvent. As the carbon is developing a positive charge, it comes in from the backside. So the result is a backside attack. This leads the game to generate the cation, and then that follows. And you generate something that looks very much like this product up here. In fact, this might be a great opportunity to just copy paste. I can get the H with it. What can you do? It's okay, it's a blue H anyway. The O there has an H on it. The HOCH3 also has an H on it. And what's going to take that H off and make our lovely vicinal ether alcohol? That's what we got. Vicinal hydroxy ether. How's that? In fact, that was up here too. Vicinal hydroxy ether and vicinal hydroxy ether. What's going to make it? Well, the only thing we have available to remove the proton is methanol. Please use it. And there you go. And I picked these as our first two examples. We'll do many others because here's the two products. They have the same functional groups. And they have complementary There's a word we used before that we're going to use again that says in one of them we put the groups in this order with the ether here on the less substituted carbon and the alcohol on the more. And in the other example, we put the ether on the more substituted carbon and the alcohol on the less substituted carbon. What do you call it when we put groups in different places? Starts with an R. Ends with a Y. It's got an S in the middle. And a TY, it's one of those TI. Ivity. Have you guessed RE? GIOELECT. They have complementary regio selectivity. Very interesting. And being able to do either thing with epoxides is important. So we're going to finish with just several other reactions, and I'm going to ask you for the mechanisms. And I'm going to ask you to circle the product formed and give the mechanism. So big finish right here. We'll do a real life example. The first one. I'm going to ask you to draw the product from here. We did one per acid before. There's 3 other per acids we have to learn, or 2 others, not 3. Looks complicated. Looks complicated. But really, there's the anion here. That's an anion. There's 2 of these anions and 1 cation. Mg is a 2+ cation, right? And you should list cations first. Don't want my inorganic chemistry friends upset with me. So we need to learn that's a per acid called short form MMPP, M standing for magnesium. And it's only got 1 peroxide on one of the carboxylic acids, not both. So we say monoperoxy. So we're through 3 of the letters. 3 of the 4 letters are accounted for. And benzene with 2 carboxylic acids are called phthalic acids. Very strange spellings. And the other phthalic is a phthalate ion. Ic acids come from 8 ions. So you got your MMPP. Magnesium monoperoxyphthalate. And that other per acid we used previously, way back. There, where was it? Blank page. I'll get rid of the blanks before I post. Apparently, we did this longer ago than I thought. Was it way back there? Yes. Peracetic acid. Just a little cautionary note. It's dangerous. If you want to use peracetic acid, you've got to follow the recipe to make peracetic acid and then immediately react it before it does other things that peracetic acid can do, often involving fire and explosions. MMPP, much safer. Nice, safe crystals to work with, which means you can easily measure out accurate amounts. and it has a nice shelf life of years. And you don't have to use it within minutes of making it. You can buy it and let it sit. Anyway, that sounds like lab stuff, doesn't it? So we should be able to predict the product, draw both enantiomers. We'll make this into an exam type problem. Draw both enantiomers. In fact, I'll just I'll put that here. I don't know. It's going to be the same per acids here. Yeah. Hang in there, Dr. Whitaker. Yeah. And here I'll say draw both enantiomers. Of course, never fits in the box when I do the box ahead of time. Okay. And the top one I want to be 1R. To S, and the bottom one I want to be, the enantiomer would have to be 1S, 2R. So that's one little exercise we're going to do. And then we'll do reactions of both those enantiomers. So why don't we draw one of them down here and then decide which part of the box I put it in. There's one of them. Did I get it all drawn at the same time? I did. Okay. Now, if that's the molecule, then doing R and S on it, realize there's an H here. And that's okay to have an H on a wedge, isn't it? Carbon 1 is here. 2 is here. Stereo centers. O is heaviest. Carbon with O, second heaviest. Carbon with O, no O, sorry, third. Methyl, fourth. It's not R, therefore it's 1S. And I'm assuming the bottom one, based on the question, would have to be 2R. Let's verify that. Let's do that in purple. Bottom stereo center, we got a 1 there, a 2 for a carbon with an O, a 3 for a carbon without an O, and a 4 for an H. So it's not S, therefore it's R. So this would be the second product, wouldn't it? 1S, 2R. And how do I fix it? Over here. What if I can flip it? Does it give me that option? It's not even giving me any options there. Flipping. All this time I'm spending, I just should redraw it. Okay. We are drawing the enantiomer. So methyl on a dash, O's both on wedges. I hope you know that both O's have to be on the same type of bond. You can't make a triangle where one part of the triangle is above the ring and the other part is below because it's the same part. You can't be in two places at the same time. So there's our two products, which we will finish our lecture with. I'm going to copy those. I can't. My box is in the way. I can copy that one. Uh-oh, I think I made a new document by mistake. Oh, this is dangerous. That should be our old document. Or it's the one we're just working on. There it is. Got some work to do at the end here. We're going to finish by giving mechanisms for each. We'll end with 3 mechanisms. Give mechanisms for each. We'll just use this one for every example. In this one, step 1 will be our old friend acetylide. Step 2, HCl. Well, that's part B. Circle the only product formed. Okay, so I'm going to give you 2 products for each one. One of the products will have OH and there, or oh, never can have the OH on a dash, or I messed up. Confession. Just get rid of the whole thing. O's got to be on a dash no matter what. Those bonds are both set. If that's on a dash, then the incoming had to be on a wedge, pushing the methyl to the back in that example. All right. Okay, that's a good one. Let's switch it up. Let's do this one. And we'll do, I don't know. We'll do KN3. Maybe we'll finish with 4. And HOET. And your 2 things will change acetylide for N3. We're going to finish with 4. No. Need another acid-catalyzed one. Acid-catalyzed one. Therapeutic, they're doing that. All right, so what do we want to do? Acid-catalyzed using HOTS. And maybe a moderate nucleophile. Nitrogen's not a good choice. There we go. Stinky propane thiol. And propyls here. S-propyls. Almost redid my typo from the exam. Okay. And our finishing one, we got to finish strong. We'll just have one thing present down here. H2N isopropyl. We'll have NH isopropyl there and NH isopropyl here. Yep, 1H, not 2. Let's do it. Last 4 pages, 1, 2, 3, 4. Do all the stuff underneath. All right. We do not have an acid, strong acid present from the beginning. I'm pointing that out right now. This has nothing to do with cations. That's a strong nucleophile in step 1. Please, in a universe where it says do this first and do this second, don't pretend the 2 happens before 1. There's a reason there's a 1 there and a 2 there. You must do 1, you must finish 1, and then you're allowed to start 2. End of story. C, triple C, H, strong nucleophile approaches the least hindered carbon. You generate an O minus. This mechanism's almost done. We have established that we're making the first product. There's your wedge acetylide attached there. The O is an O minus. This is the end of step 1. Over, done, finished. Now you do step 2. Provide a proton for that species to become its conjugate acid. That's all HCl is doing here. Step 2. Can't be done during step 1. Done. Not too bad, right? This one. I don't see a strong acid present here. Do you? At all? Yes. Oh, sorry. I apologize. I see a strong acid here. I see HOTS. I'm thinking cations immediately. This is a medium nucleophile, but there's a strong acid present. It is the most important thing. You will have a strong acid react ahead of a moderate nucleophile every day of the week. And there we go. Dramatic finishing music. I don't know if you can hear it. Cation. You should be thinking about which carbon spends more time with the positive charge. Top one, tertiary, or bottom one, secondary. Top one, tertiary, gets hit backside with the nucleophile. OH, quote unquote, leaves, but it doesn't leave. It's still attached on the bottom. We've got the OH. We got the salt. Oh, no, it's we're talking about this one. We got this OH. We got our sulfur on a wedge. We got the methyl pushed back on a dash. This is the conjugate base of the, conjugate acid of the second product. What is going to take the H? You generated TSO minus in step 1. When you protonated the ether, the epoxide ether. TSO minus comes and grabs that H. S gets its lone pair. That's a very tiny arrow. There, it's a nice arrow. See if yeah, we got a whole deal. And this was our product with the S on the more substituted carbon. If I wanted to put the S on the less substituted carbon, I would have done two very simple things. I'd use S minus, a strong nucleophile, and some other way to get the proton on there. Maybe step 2 HCl like last time. That's one way to do it. In fact, let's just do it. Just pretend that's a box. And the answer for that box is less substituted carbon backside attack. It's the first product listed there above. Oh my goodness, what's going on? We got a dashed OH. We reversed the regioselectivity, didn't we? Good for us. And the big finish. You're saying, wait, we don't have enough chemicals in this one. How do I do it? Well, let's follow the prediction rules first. The prediction rules say, do I have a strong acid present? No. So I've got to use the nucleophile approach. I have a moderate nucleophile and no strong acid. Mod nu. More important, no strong acid. So it's about approach, isn't it? Do you see cations? I don't see a cation. Don't be using cation thinking for a reaction that doesn't use cations. Think about steric hindrance. Which carbon's easier to approach? And it's the bottom one, isn't it? Big finish. It's very exciting. O minus somehow has to become OH. What's the pKa of an OH, by the way? Oh yeah, it's an alcohol up there. 17. What's the pKa of this acid I'm about to draw? It's an N with 4 bonds. And at least one of them is an H. pKa 10. You can't have a reaction with an acid, a product that has a pKa of 10 where the potential of having a pKa of 17 is in the same molecule. 10 always goes towards 17. You can't stop it. This thing does an intramolecular proton transfer. And you're asking, can that O reach that H? And it sure can. The ring size as it's reaching in the transition state, the ring size has how many atoms? 1, 2, 3, 4, 5. 5's nice. If it was smaller, there'd be strain in the reaching and it wouldn't happen. We'll talk about that in Orgo too. And that's that product right there. And we have a lot of good examples of nucleophilic epoxide opening and acid-catalyzed epoxide opening. And thank you for making it all the way through the semester. You are all champions for even making it this far. And I hope to see you all again really soon, like really see you too soon. And my best wishes to all of you and your families, and good luck in your future studies. Thank you.